Atomic structure. Atoms are the building blocks of all matter. They consist of a small dense positively charged nucleus and negatively charged electrons in orbit around the nucleus. Atomic structure. An atom is a small positive nucleus, surrounded by orbiting negative electrons. Atoms are incredibly small, with a radius of only 1 × 10 to 10 m. This means that about 100 million atoms could fit side by side across your thumbnail. The radius of the nucleus is over 10,000 times smaller than the whole atom, but it contains almost all of the mass of the atom. Rutherford's alpha scattering experiment. Extended tier only. In Rutherford's alpha scattering experiment, the scattering of alpha particles by a sheet of thin metal supports the nuclear model of the atom, by providing evidence for a very small nucleus surrounded by mostly empty space. A nucleus containing most of the mass of the atom. A nucleus that is positively charged. In 1909, a group of scientists were investigating the plum pudding model of atomic structure. Physicist Ernest Rutherford was instructing 2 of his students, Hans Geiger and Ernest Marsden, to carry out the alpha scattering experiment. They directed a beam of alpha particles, He2+ ions, at a thin gold foil. They expected the alpha particles to travel through the gold foil, and maybe change direction a small amount. As shown in the diagram, instead they discovered that most of the alpha particles passed straight through the foil because the atom is mostly empty space A. Some of the alpha particles changed direction but continued through the foil because the positive nucleus repels the positive alpha particles B. A few of the alpha particles bounced back off the gold foil because the nucleus is tiny. This bouncing back could not be explained by the plum pudding model of atomic structure, so a new model had to be created. This was the first evidence of the nuclear atom as atomic structure. Rutherford's alpha scattering experiment results. When alpha particles are fired at thin gold foil, most of them go straight through but a very small number bounce straight back. Atoms and ions. An ion is an electrically charged atom or group of atoms formed by the loss or gain of electrons. An atom will lose or gain electrons to become more stable. A stable atom is normally electrically neutral. This means it has the same number of protons positive charge and electrons negative charge. Positive ions are therefore formed when atoms lose electrons. There will be more protons than electrons. Negative ions are therefore formed when atoms gain electrons. There will be more electrons than protons. The atomic structure of ions. The difference between positive and negative ions. Exam tip. You may hear the term net charge. This just means the overall charge of the atom. If an atom has 5 protons, 5 neutrons and 6 electrons, it has a net negative charge because it's a negative ion, more electrons than protons. Remember which way around the charges are by proton being positive. Composition of the nucleus. A nucleus is composed of positively charged protons, neutrally charged neutrons. Hence a nucleus has an overall positive charge. Structure of the atom. Protons and neutrons are found in the nucleus of an atom. Did this video help you? Yes. No. Exam tip. Be careful with your terminology. Atom equals nucleus, proton and neutron, and electrons. Nucleus equals protons and neutrons at the center of the atom. Describing the nucleus. Proton number, Z. The number of protons in an atom is called its proton number. It can also be called the atomic number. Elements in the periodic table are ordered by their atomic number. Therefore, the number of protons determines which element an atom is. The atomic number of a particular element is always the same. For example, hydrogen has an atomic number of 1. It always has just 1 proton. Sodium has an atomic number of 11. It has 11 protons. Uranium has an atomic number of 92. It has 92 protons. The atomic number is also equal to the number of electrons in an atom. This is because atoms have the same number of electrons and protons in order to have no overall charge. Nucleon number, A. The total number of particles in the nucleus of an atom is called its nucleon number or mass number. The mass number is the number of protons and neutrons in the atom. Calculating the number of neutrons. The number of neutrons can be found by subtracting the atomic number from the mass number. For example, if a sodium atom has a mass number of 23 and an atomic number of 11, then the number of neutrons would be 23 to 11 equals 12. Exam tip. You may have noticed that the number of electrons is not part of the mass number. This is because electrons have a tiny mass compared to neutrons and protons. We say their mass is negligible when compared to the particles in the nucleus. Nuclide notation. Atomic symbols are written in a specific notation called ZXA or nuclide notation. The top number A represents the nucleon number. The lower number Z represents the proton number. Nuclide notation. Atomic symbols in AZX nuclide notation describe the constituents of nuclei. A nuclide is a group of atoms containing the same number of protons and neutrons. For example, 5 atoms of oxygen are all the same nuclide but are 5 separate atoms. An example of nuclide notation is example of lithium nuclide notation. Atomic symbols, like the one above, describe the constituents of nuclei. Worked example. The element symbol for gold is O. How many protons, neutrons and electrons are in the gold atom? Protons, neutrons, electrons. A. 79, 79, 79. B. 197, 79, 118. C. 118, 118, 79. D. 79, 118, 79. Answer. D. Step 1. Determine the atomic and mass number. The gold atom has an atomic number of 79 lower number and a mass number of 197 top number. Step 2. Determine the number of protons. The atomic number is equal to the number of protons. The atom has 79 protons. Step 3. Calculate the number of neutrons. The mass number is equal to the number of protons and neutrons. The number of neutrons is equal to the mass number minus the atomic number. The atom has 118 neutrons. Step 4. Determine the number of electrons. An atom has the same number of protons and electrons. The atom has 79 electrons. Exam tip. You may recognize this notation from the periodic table in chemistry when mass number and proton number are more commonly used. In physics, you are more likely to see nucleon number and proton number. The periodic table is ordered by atomic number. Did this video help you? Yes. No. Isotopes. Although the number of protons in a particular element is always the same, the number of neutrons can be different. Isotopes are atoms of the same element that have an equal number of protons but a different number of neutrons. This means that each element can have more than one isotope. Isotopes tend to be more unstable due to their imbalance of protons and neutrons. This means they're more likely to decay. In the diagram below are 3 isotopes of hydrogen. Isotopes of hydrogen. Hydrogen has 3 isotopes, each with a different number of neutrons. Isotopes occur naturally, but some are more rare than others. For example, about 2 in every 10,000 hydrogen atoms is deuterium. Tritium is even more rare, about 1 in every billion hydrogen atoms. Worked example. Which of the following elements are isotopes of each other? A, and, B, and, C, and, D, and. Answer. B. In nuclide notion, the top number is the nucleon number of protons and neutrons, and the bottom number is the proton number of protons. Isotopes are 2 of the same elements. This eliminates option D since one is oxygen O and the other nitrogen N, which have the same number of protons. This eliminates option C and A. Their proton numbers are different for the same element, but a different number of neutrons. Therefore, the correct answer is B. Relative charge. Charge can be positive or negative. Protons, neutrons and electrons have different properties and different charges. Protons have a positive charge. Electrons have a negative charge. Neutrons have no charge. Relative charge can be used to compare these properties. Relative charge is the ratio of the charge of a particle compared to the fundamental charge. Because relative charge is a ratio, it has no units. Fundamental charge is equal to the magnitude of the charge on a proton, and an electron equals 1.6 times 10⁻19 c. The relative charge of a proton is. The relative charge of an electron is. The relative charge of a neutron is. Table of relative charges. Particle, relative charge, proton, +1, neutron, 0, electron, -1. Exam tip. You don't need to know how to calculate relative charge, but you do need to understand what it is. You do also need to remember what the relative charges are for each subatomic particle. Nuclear charge. Extended tier only. Nuclear charge is the relative charge of the nucleus. This is determined by the proton number of the atom. Relative charge is calculated by an element of carbon has a proton number of 6. So the relative charge of carbon is 6 times +1 equals 6. Worked example. What is the relative charge of the chromium nucleus? Answer. Step 1. Determine the number of protons. The number of protons is the proton number. This is the Z number in the AZX notation. This chromium nucleus has 24 protons. Step 2. State the relative mass of one proton. One proton has a relative charge of +1. Step 3. Multiply relative charge of one proton by the number of protons. This nucleus of chromium therefore has a relative charge of +24. Exam tip. Charge can be either positive, plus, or negative. Usually, when a number is positive, we don't write the plus sign, but when dealing with relative charge, we do. Nuclear mass. Extended tier only. Nuclear mass, or the relative mass of an atom, is the relative mass of the nucleus. This is because the mass of electrons orbiting the nucleus is negligible. A relative mass of 1 equals 1.67 times 10 to 27 kg. The relative mass of an atom is determined by the nucleon number of the atom. It is calculated by an element of carbon has a nucleon number of 12. So the relative mass of carbon is 12 times 1 equals 12 atomic mass units, or AMU. Table of relative mass. Particle, relative mass, proton, 1, neutron, 1, electron, negligible. Worked example. What is the relative mass of the chromium nucleus? Answer. Step 1. Determine the number of protons and neutrons. The number of protons and neutrons is the mass nucleon number. This is the A number in the AZX notation. This chromium nucleus has 52 protons and neutrons. Step 2. State the relative mass of one proton and one neutron. One proton has a relative mass of 1. One neutron has a relative mass of 1. Step 3. Multiply relative charge of one proton and one neutron by number of protons and neutrons. This nucleus of chromium therefore has a relative mass of 52. Exam tip. The relative mass of a nucleus only includes the protons and neutrons. However, this is pretty much the relative mass of the whole atom because electrons have negligible, very little, mass in comparison to the proton and neutron. Fission and fusion. Nuclear fission and fusion are nuclear reactions that change the nucleus of an atom to produce high amounts of energy from the energy stored in the nucleus of an atom. Nuclear fission. Nuclear fission is defined as the splitting of a large, unstable nucleus into two smaller nuclei. During fission, a neutron collides with an unstable nucleus. The neutron and the nucleus are the reactants. The nucleus splits into two smaller nuclei called daughter nuclei and 2 or 3 neutrons. The daughter nuclei and the neutrons are the products of the reaction. Gamma rays are also emitted. Nuclear fission process. A neutron is fired into the target nucleus, causing it to split. Nuclear fission nuclide equations. An example of a nuclide equation for the fission of uranium-235 is: where is an unstable isotope of uranium? Is a neutron. Is an unstable isotope of krypton. Is an unstable isotope of barium. Nuclear fission of uranium-235. Large nuclei can decay by fission to produce smaller nuclei and neutrons with a lot of kinetic energy. Nuclear fission mass and energy values. Energy is conserved in a nuclear fission reaction. In the example, the sum of the nucleon top numbers of the reactant's left-hand side is equal to the sum of the nucleon numbers of the product's right-hand side. The same is true for the proton bottom numbers. The products of fission move away very quickly. During a fission reaction, energy is transferred from nuclear energy store of the parent nucleus to the kinetic energy store of the reactants. The mass of the products is less than the mass of the original nucleus. This is because the remaining mass has been converted into energy, which is released during the fission process. Large isotopes with a large nucleon number, such as uranium and plutonium, both undergo fission and are used as fuels in nuclear power stations. Nuclear fusion. Nuclear fusion is defined as when two light nuclei join to form a heavier nucleus. Stars use nuclear fusion to produce energy. In most stars, hydrogen nuclei, light nuclei, are fused together to form a helium nucleus, heavier nucleus, and massive amounts of energy is produced. Nuclear fusion of hydrogen. Two hydrogen nuclei fuse to form a helium nucleus. Nuclear fusion requires extremely high temperature and pressure. So fusion is very hard to reproduce on Earth. Nuclear fusion nuclide equations. An example of a nuclide equation for fusion is where is deuterium isotope of hydrogen with 1 proton and 1 neutron. Is hydrogen with 1 proton. Is an isotope of helium with 2 protons and 1 neutron. Nuclear fusion mass and energy values. The energy produced during nuclear fusion comes from a very small amount of a particle's mass converted into energy. Albert Einstein described the mass-energy equivalence of nuclear fusion with his famous equation, where E equals energy released from fusion, measured in joules J. M equals mass converted into energy, measured in kilograms kilogram. C equals the speed of light, measured in meters per second meter per second. Therefore, the mass of the product fused nucleus is less than the mass of the two original nuclei reactants. The remaining mass has been converted into the energy released when the nuclei fuse. The amount of energy released during nuclear fusion is huge. The energy from 1 kilogram of hydrogen that undergoes fusion is equivalent to the energy from burning about 10 million kilograms of coal. Did this video help you? Yes. No. Worked example. A nuclide equation for nuclear fission is stated as calculate the number of neutrons N emitted in this reaction. Answer. Step 1. Calculate the sum of the nucleon numbers of the reactants. The reactants are on the left-hand side of the equation. The nucleon numbers are the top numbers in the nuclide notation. 235 plus 1 equals 236. Step 2. Calculate the sum of the nucleon numbers of the products. The products are on the right-hand side of the equation. 96 plus 137 plus n times 1 equals 233 plus n. Step 3. Equate the total nucleons of the reactants and products. 236 equals 233 plus n. Step 4. Rearrange for the number of neutrons, n. N equals 236 to 233 equals 3. Background radiation. Background radiation is defined as the radiation that exists around us all the time. There are two types of background radiation. Natural sources from radioactive elements that have always existed on Earth and in outer space. Man-made sources from human activity that adds to the amount of radiation humans are exposed to on Earth. The count rate of detected levels of background radiation can vary significantly from place to place. Sources of background radiation. The sources that make a significant contribution to background radiation include radon gas in the air, rocks and buildings, food and drink, cosmic rays. Sources of background radiation. Background radiation is the radiation that is present all around in the environment. Radon gas is given off from some types of rock. Natural sources. Rocks and buildings. Natural radioactivity can be found in building materials, including decorative rocks, stone and brick. Heavy radioactive elements, such as uranium and thorium, occur naturally in rocks in the ground. Uranium decays into radon gas. Radon gas in the air. Radon gas is an alpha emitter. Radon gas is particularly dangerous if it is inhaled into the lungs in large quantities. The gas is tasteless, colorless and odorless, but it is not generally a health issue unless levels are significantly high. Radioactive material in food and drink. Naturally occurring radioactive elements can get into food and water since they are in contact with rocks and soil containing these elements. Some foods contain higher amounts such as potassium-40 in bananas. However, the amount of radioactive material is minuscule and is not a cause for concern. Cosmic rays from space. The Sun emits an enormous number of protons every second. Some of these enter the Earth's atmosphere at high speeds. When they collide with molecules in the air, this leads to the production of gamma radiation. Other sources of cosmic rays are supernovae and other high-energy cosmic events. Carbon-14 in biological material. All organic matter contains a tiny amount of carbon-14. Living plants and animals constantly replace the supply of carbon in their systems, hence the amount of carbon-14 in the system stays almost constant. Man-made sources. Medical sources. In medicine, radiation is used frequently. Uses include X-rays, CT scans, radioactive tracers, and radiation therapy. Nuclear waste. While nuclear waste itself does not contribute much to background radiation, it can be dangerous for the people handling it. Nuclear fallout from nuclear weapons. Fallout is the residue radioactive material that is thrown into the air after a nuclear explosion, such as the bomb that exploded at Hiroshima. While the amount of fallout in the environment is presently very low, it increases significantly in areas where nuclear weapons are tested. Nuclear accidents. Accidents such as that in Chernobyl contributed a large dose of radiation into the environment. While these accidents are now extremely rare, they can be catastrophic and render areas devastated for centuries. Exam tip. The sources that make the most significant contribution are the natural sources. Radon gas. Rocks and buildings. Food and drink. Cosmic rays. Make sure you remember these for your exam. Detecting radiation. Ionizing nuclear radiation can be measured using a detector connected to a counter. Count rate. The detector uses count rate measured in counts s or counts per minute. The count rate is the number of decays per second. The count rate decreases the further the detector is from the source. This is because the radiation becomes more spread out the further away it is from the source. Geiger-Müller tube detects count rate. The Geiger-Müller tube is the most common device used to measure and detect the count rate of radiation. Each time it absorbs radiation, it transmits an electrical pulse to a counting machine. This makes a clicking sound and it displays the count rate on a screen. The greater the frequency of clicks, or the higher the count rate, the more radiation the Geiger-Müller tube is absorbing. Therefore, it matters how close the tube is to the radiation source. The further away from the source, the lower the count rate detected. Geiger-Müller tube detects count rate. A Geiger-Müller tube, or Geiger counter, is a common type of radiation detector detecting count rate. Examples of other radiation detectors include photographic film, often used in badges, ionization chambers, scintillation counters, spark counters. Worked example. A Geiger-Müller tube is used to detect radiation in a particular location. What is the count rate if it counts 16,000 decays in 1 hour? Answer. Step 1. Identify the different variables. The number of decays is 16,000. The time is 1 hour. Step 2. Determine the time period in seconds. 1 hour is equal to 60 minutes, and 1 minute is equal to 60 seconds. Step 3. Divide the total counts by the time period in seconds. Therefore, there are 4.5 decays per second. Exam tip. If asked to name a device for detecting radiation, the Geiger-Müller tube is a good example to give. You can also refer to it as a GM tube, a GM detector, GM counter, Geiger counter, etc. The examiners will allow some level of misspelling, providing it is readable. Don't, however, refer to it as a radiation detector, as this is too vague and may simply restate what was asked for in the question. It is important to regulate the exposure of humans to radiation. The amount of radiation received by a person is called the dose. Accounting for background radiation. Extended tier only. Measurements of background radiation are used to determine a corrected count rate. This can be done by taking readings with no radioactive source present and then subtracting this from readings with the source present. Did this video help you? Yes. No. Worked example. A student is using a Geiger counter to measure the counts per minute at different distances from a source of radiation. Their results and a graph of the results are shown here. Determine the background radiation count. Answer. Step 1. Determine the point at which the source radiation stops being detected. The background radiation is the amount of radiation received all the time. When the source is moved back far enough, it is all absorbed by the air before reaching the Geiger counter. Results after 1 meter do not change. Therefore, the amount after 1 meter is only due to background radiation. Step 2. State the background radiation count. The background radiation count is 15 counts per minute. Radioactive decay. The emission of radiation from a nucleus is spontaneous and random in direction. This random process of radioactive decay means there is an equal probability of any nucleus decaying. It cannot be known which particular nucleus will decay next. It cannot be known at what time a particular nucleus will decay. The rate of decay is unaffected by the surrounding conditions. It is only possible to estimate the probability of a nuclei decaying in a given time period. Unstable nuclei. Some atomic nuclei are unstable. This is because of an imbalance in the forces within the nucleus. Forces exist between the particles in the nucleus. Instability is commonly due to the nucleus having too many protons or neutrons. The nucleus being very large. An example of an unstable nucleus is carbon-14. This is an isotope of carbon. It has 2 extra neutrons compared to stable carbon-12. Isotopes of carbon. Carbon-12 is stable, whereas carbon-14 is unstable. This is because carbon-14 has 2 extra neutrons. Unstable nuclei can emit radiation to become more stable. Radiation can be in the form of a high-energy particle or wave. Unstable nuclei emit radiation. Unstable nuclei decay by emitting high-energy particles or waves. As the radiation moves away from the nucleus, it takes some energy with it. This reduces the overall energy of the nucleus. This makes the nucleus more stable. Worked example. Which of the following statements is not true? Isotopes can be unstable because they have too many or too few neutrons. B. The process of emitting particles or waves of energy from an unstable nucleus is called radioactive decay. C. Scientists can predict when a nucleus will decay. D. Radiation refers to the particles or waves emitted from a decaying nucleus. Answer. C. Consider what you know about the statements above. Isotopes. Radioactive decay. Nuclei decay prediction. Radiation. Answer A is true. The number of neutrons in a nucleus determines the stability. Answer B is true. This is a suitable description of radioactive decay. Answer D is true. Radiation is about emissions. It is different to radioactive particles. Answer C is not true. Radioactive decay is a random process. It is not possible to predict precisely when a particular nucleus will decay. Exam tip. The terms unstable, random and decay have very particular meanings in this topic. Remember to use them correctly when answering questions. Types of radioactive decay. Radioactive decay is a change in an unstable nucleus that can result in the emission of one of the following types of radiation. Alpha particles. Beta particles. Gamma radiation. Remember that these changes are spontaneous and random. Alpha particles. The radiation symbol for alpha is alpha. An alpha particle is the same as a helium nucleus. This is because they consist of 2 neutrons and 2 protons. Alpha particles have a charge of +2. This means they can be affected by an electric field. Beta particles. The radiation symbol for beta is beta. Beta particles are fast-moving electrons. They are produced in nuclei when a neutron changes into a proton and an electron. Beta particles have a charge of -1. This means they can be affected by an electric field. Gamma rays. The radiation symbol for gamma is gamma. Gamma rays are electromagnetic waves. They have the highest energy of the different types of electromagnetic waves. Gamma rays have no charge. Types of radioactive decay. Alpha particles, beta particles and gamma waves can be emitted from unstable nuclei. Alpha, beta and gamma emission. Alpha, beta and gamma radiation can be identified by the emission from a nucleus by recalling their nature, what type of particle or radiation they are. Their relative ionizing effects, how easily they ionize other atoms. Their relative penetrating abilities, how far can they travel before they are stopped completely. The properties of alpha, beta and gamma are given in the table, which shows the trend down the table as the range increases, penetrating power increases, ionization decreases. Summary of the properties of nuclear radiation. Particle, nature, range in air, penetrating power, ionizing ability. Alpha, helium nucleus, 2 protons, 2 neutrons. A few cm. Low, stopped by a thin sheet of paper. High, beta, high energy electron. A few tens of cm. Moderate, stopped by a few of aluminium foil or perspex. Moderate. Gamma, gamma, electromagnetic wave. Infinite. High, reduced by a few cm of lead. Low, penetrating power. Alpha, beta and gamma radiation have different properties, so they penetrate materials in different ways. This means they are each stopped by different materials. Penetrating power of alpha, beta and gamma radiation. Alpha, beta and gamma are different in how they penetrate materials. Alpha is the least penetrating, and gamma is the most penetrating. Alpha is stopped by paper, whereas beta and gamma pass through it. Beta is stopped by a few millimeters of aluminium. Gamma can pass through aluminium. Gamma rays are only partially stopped by thick lead. Worked example. A student has an unknown radioactive source. They are trying to work which type of radiation is being given off. A alpha particles, B beta particles, C gamma rays, D neutrons. They measure the count rate, using a Geiger-Müller tube, when the source is placed behind different material. Their results are shown in the table below. No material between source and detector. Paper between source and detector. 5 mm aluminium between source and detector. 5 mm lead between source and detector. Count rate. 4,320. 4,218. 256. 34. Which type of radiation is being given off by the source? Answer. B. Consider the diagram showing penetrating power from above. The answer is not A because the radiation passed through the paper almost unchanged. This means it is not alpha. The answer is not C or D because the aluminium decreased the count rate significantly. This means it is not gamma. Gamma penetrates aluminium. This also means it is not neutrons. Neutrons penetrate aluminium, however you do not need to know this for your GCSE. Therefore, the source must be beta particles. Exam tip. Remembering the type of particle, penetration and ionizing power for alpha, beta and gamma radiation is very important for your exam. Often the exam question will give some clues and you will have to choose which type of radiation it could be based off these. Ionizing effect of radiation. Extended tier only. The relative ionizing effects of nuclear radiation depend upon their kinetic energy, electric charge, ionization. Ionization is when an atom becomes negatively or positively charged by gaining or losing electrons. Nuclear radiation can ionize the atoms that it hits. This is mostly done by removing an electron so the atom loses a negative charge and is left with an overall positive charge. Nuclear radiation ionizing an atom. When radiation passes close to atoms it can knock out electrons, ionizing the atom. Effects of kinetic energy and charge on ionizing power. The greater the charge of the radiation, the more ionizing it is. This means alpha radiation is the most ionizing as it has a charge of +2. A beta particle has a charge of -1 so it is moderately ionizing. This means gamma radiation is the least ionizing as it has a charge of 0, no charge. The higher the kinetic energy of the radiation, the more ionizing it is. This means the alpha particle is still the most ionizing because it has the greatest mass. However, a beta particle is very light, it is an electron but travels at high speeds, therefore, it has a lot of kinetic energy and is still moderately ionizing. Gamma radiation has virtually no mass so it is weakly ionizing. Exam tip. Remembering the properties of alpha, beta and gamma radiation helps to deduce how much ionizing power they have. E.g., an alpha particle is a helium nucleus which contains 2 protons and 2 neutrons. It therefore has a charge of +2 since each proton has a charge of +1 and a neutron has no charge. Kinetic energy is defined by the equation mv2 therefore it depends on the mass m of the particle and its velocity versus deflection in electric and magnetic fields. Extended tier only. Alpha particles, beta particles and gamma radiation are deflected differently in electric and magnetic fields. A particle is deflected in an electric field if it has charge. A particle is deflected in a magnetic field if it has charge and is moving perpendicular to it. Therefore, since gamma particles have no charge, they are not deflected by either electric or magnetic fields. Only alpha and beta particles are deflected. Electric fields. Alpha particles have a charge of +2, the charge of a helium nucleus. Beta particles have a charge of -1, the charge of an electron. Therefore, in an electric field created between negatively and positively charged plates, alpha particles are deflected towards the negative plate. Beta particles are deflected towards the positive plate. Gamma radiation is not deflected and travels straight through between the plates. Deflection in electric fields. Alpha and beta particles can be deflected by electric fields. Alpha particles are heavier than beta particles. Therefore, beta particles are deflected more in the electric field. Magnetic fields. Similarly, alpha and beta particles are deflected by magnetic fields whilst they are moving. They are deflected in opposite directions due to their opposite charges. Deflection of a beta particle in a magnetic field. Alpha and beta particles can also be deflected by magnetic fields. Exam tip. It is important to note that because of their opposite charges, alpha and beta particles will deflect in opposite directions. You do not need to know which direction alpha and beta particles are deflected in a magnetic field, this is covered at A level, but you should know that they are deflected, whilst gamma is not because they are charged and they deflect in opposite directions. Effect of nuclear size on decay. Extended tier only. Isotopes of an element may be radioactive due to an excess of neutrons in the nucleus and/or the nucleus being too heavy. Excess of neutrons. The most stable nuclei have roughly the same number of protons as neutrons. Too many protons in a nucleus means the repulsive force between them is large, causing the neutrons to repel each other. So, a nucleus with an imbalance of protons or neutrons is more likely to decay into several smaller nuclei until stable nuclei are obtained, with roughly the same number of nucleons in each nucleus. An example of this is the isotope of hydrogen -1. H-1 is the stable nucleus of hydrogen with 0 neutrons and 1 proton. H2 deuterium has 1 more neutron in the nucleus. H3 tritium has 2 neutrons to 1 proton. This is much more unstable than H-1 or H2. Hydrogen isotopes. Heavy nucleus. If a nucleus is too heavy, this means it has too many protons and neutrons. The forces keeping the protons and neutrons together in the nucleus will be weaker. An example of this is uranium-238. It has a nucleus with 238 protons and neutrons. During nuclear decay, the mass number of the element which it decays into is gradually reduced. This is done through alpha or beta decay. Uranium-238 decay chain. The graph shows the decay chain of uranium-238 through alpha and beta emission. Exam tip. The notation of C12, for example, means the element, carbon, with the mass or nucleon number of 12. Change to a new element. A nucleus changes to a different element during alpha decay or beta decay. The initial nucleus is often called the parent nucleus. The nucleus of the new element produced is often called the daughter nucleus. The daughter nucleus is a new element because it has a different proton and/or nucleon number than the original parent nucleus. This can be seen on a graph of N neutron number against Z proton number. For example, when Pu-239 decays by alpha to U-235, it loses 2 protons and 2 neutrons. Uranium is a completely different element from plutonium. Graph of neutron number against proton number. Graph of N against Z for the decay of Pu-239. Reducing neutron number. Extended tier only. Alpha and beta decay affect the nucleus by increasing its stability, reducing the number of excess neutrons. Alpha decay. During alpha decay, an alpha particle is emitted from an unstable nucleus. A completely new element is formed in the process. Alpha decay. Alpha decay usually happens in large unstable nuclei, causing the overall mass and charge of the nucleus to decrease. An alpha particle is a helium nucleus. It is made of 2 protons and 2 neutrons. When the alpha particle is emitted from the unstable nucleus, the mass number and atomic number of the nucleus changes. The mass number decreases by 4. The atomic number decreases by 2. The charge on the nucleus also decreases by 2. This is because protons have a charge of +1 each. Beta decay. During beta decay, a neutron changes into a proton and an electron. The electron is emitted and the proton remains in the nucleus. A completely new element is formed because the atomic number changes. Beta decay. Beta decay often happens in unstable nuclei that have too many neutrons. The mass number stays the same, but the atomic number increases by 1. A beta particle is a high-speed electron. It has a mass number of 0. This is because the electron has a negligible mass, compared to neutrons and protons. Therefore, the mass number of the decaying nucleus remains the same. Electrons have an atomic number of -1. This means that the new nuclei will increase their atomic number by 1, so atomic number is conserved before and after the decay. Gamma decay. During gamma decay, a gamma ray is emitted from an unstable nucleus. This process makes the nucleus less energetic but does not change its structure because gamma radiation has no mass or charge. Gamma decay. Gamma decay does not affect the mass number or the atomic number of the radioactive nucleus, but it does reduce the energy of the nucleus. Exam tip. There is a second form of beta decay during which a proton changes into a neutron. This is called beta plus decay. You might come across it while revising, but you don't need to know about it for your exam. Only use the information here for your IGCSE. It is easy to forget that an alpha particle is a helium nucleus, or that a beta particle is an electron. Look out for either wording. Decay equations. Extended tier only. Decay equations use nuclide notation to show the emission of alpha particles, beta particles and gamma radiation. A decay equation is similar to a chemical reaction equation. The particles present before the decay are shown before the arrow. The particles produced in the decay are shown after the arrow. During decay equations, the sum of the mass and atomic numbers before the reaction must be the same as the sum of the mass and atomic numbers after the reaction. Alpha decay equation. All alpha decay equations have the following form for isotopes X and Y. The following decay equation shows polonium-212 undergoing alpha decay. It forms lead-208 and an alpha particle. An alpha particle can also be written as a helium-heat nucleus. Did this video help you? Yes. No. Beta decay equation. All beta decay equations have the following form for isotopes X and Y. Did this video help you? Yes. No. Gamma decay equation. All gamma decay equations have the following form for isotope X. Worked example. A nucleus with 84 protons and 126 neutrons undergoes alpha decay. It forms lead, which has the element symbol Pb. A, B, C, D. Which isotope of lead pictured as the correct one formed during the decay? Answer. A. Step 1. Calculate the mass number of the original nucleus. The mass number is equal to the number of protons plus the number of neutrons. The original nucleus has 84 protons and 126 neutrons. The mass number of the original nucleus is 210. Step 2. Calculate the new atomic number. The alpha particle emitted is made of 2 protons and 2 neutrons. Protons have an atomic number of 1, and neutrons have an atomic number of 0. Removing 2 protons and 2 neutrons will reduce the atomic number by 2. The new nucleus has an atomic number of 82. Step 3. Calculate the new mass number. Protons and neutrons both have a mass number of 1. Removing 2 protons and 2 neutrons will reduce the mass number by 4. The new nucleus has a mass number of 206. Worked example. A nucleus with 11 protons and 13 neutrons undergoes beta decay. It forms magnesium, which has the element symbol Mg. A, B, C, D. Which is the correct isotope of magnesium formed during the decay? Answer. D. Step 1. Calculate the mass number of the original nucleus. The mass number is equal to the number of protons plus the number of neutrons. The original nucleus has 11 protons and 13 neutrons. The mass number of the original nucleus is 24. Step 2. Calculate the new atomic number. During beta decay, a neutron changes into a proton and an electron. The electron is emitted as a beta particle. The neutron has an atomic number of 0 and the proton has an atomic number of 1. So the atomic number increases by 1. The new nucleus has an atomic number of 12. Step 3. Calculate the new mass number. Protons and neutrons both have a mass number of 1. Changing a neutron to a proton will not affect the mass number. The new nucleus has a mass number of 24, the same as before. Exam tip. You are not expected to know the names of the elements produced during radioactive decays, but you do need to be able to calculate the mass and atomic numbers by making sure they are balanced on either side of the reaction. Half-life basics. The half-life of a particular isotope is defined as the time taken for half the nuclei of that isotope in any sample to decay. The rate at which the activity of a sample decreases is measured in terms of half-life. This is the time it takes for the activity of a sample to fall to half its original level. This is the time it takes for the activity of the sample to decrease from 100% to 50%. It is the same length of time as it would take to decrease from 50% activity to 25% activity. Different isotopes have different half-lives, and half-lives can vary from a fraction of a second to billions of years in length. The half-life is constant for a particular isotope. Representing half-life. Half-life can be determined from an activity time graph. A half-life graph. The graph shows how the activity of a radioactive sample changes over time. Each time the original activity halves, another half-life has passed. Half-life can also be represented on a table. As the number of the half-life increases, the proportion of the isotope remaining halves. Table showing the number of half-lives to the proportion of isotope remaining. Number of half-lives. Proportion of isotope remaining. 0, 1, 1, 2, 3, 4, ... Did this video help you? Yes. No. Worked example. An isotope of protactinium-234 has a half-life of 1.17 minutes. Calculate the amount of time it takes for a sample to decay from a mass of 10 mg to 2.5 mg. Answer. Step 1. Calculate the fraction of the sample remaining. Initial mass of sample equals 10 mg. Final mass of sample equals 2.5 mg. The fraction of the sample remaining is. Step 2. Calculate the number of half-lives that have passed. Using the table above, we can see that 2 half-lives have passed. Step 3. Calculate the time for the sample to decay. 2 half-lives have passed. So the time for the sample to decay is twice the half-life. The time for the sample to decay to a mass of 2.5 mg is 2.34 minutes. Half-life graphs. Extended tier. Only. The half-life of an isotope should be calculated by removing the background radiation from data decay curves. To calculate the half-life of a sample from a graph, check the original activity or count rate where the line crosses the y-axis CO. Have this value and look for this activity. Go across from the halved value on the y-axis to the best fit curve, and then straight down to the x-axis. The point where you reach the x-axis should be the half-life. Obtaining half-life from a half-life graph. To find the time for the half-life, find half of the activity first. To remove background radiation from the decay curve, start by measuring the background radiation with no sources present. This is called the background count. Then carry out the experiment. Subtract the background count from each reading to provide a corrected count. The corrected count is your best estimate of the radiation emitted from the source and should be used to measure its half-life. A half-life graph that removes background radiation. When measuring radioactive emissions, some of the detected radiation will be background. Worked example. The radioisotope technetium is used extensively in medicine. The graph below shows how the activity of a sample varies with time. Determine the half-life of this material. Answer. Step 1. Draw lines on the graph to determine the time it takes for technetium to drop to half of its original activity. Worked example. A particular radioactive sample contains 2 million undecayed atoms. After a year, there is only 500,000 atoms left undecayed. What is the half-life of this material? Answer. Step 1. Calculate how many times the number of undecayed atoms has halved. There were 2 million atoms to start with. 1 million atoms would remain after 1 half-life. 500,000 atoms would remain after 2 half-lives. Therefore, the sample has undergone 2 half-lives. Step 2. Divide the time period by the number of half-lives. The time period is a year. The number of half-lives is 2. So 1 half-life is 6 months. Therefore, the half-life of the sample is 6 months. Exam tip. When looking for the corresponding time for the activity, it is good practice to draw a line on the graph with your ruler like as done in the mark scheme of the worked example. This ensures you're reading the most accurate value possible. Uses of radiation. Extended tier only. The type of radiation emitted and the half-life of an isotope determine which isotope is used for the following applications. Household fire, smoke alarms. Irradiating food to kill bacteria. Sterilization of equipment using gamma rays. Measuring and controlling thicknesses of materials with the choice of radiations used linked to penetration and absorption. Diagnosis and treatment of cancer using gamma rays. Household fire alarms are a use of alpha radiation. Alpha particles are used in smoke detectors. The alpha radiation ionizes the air within the detector, creating a current. The alpha emitter is blocked when smoke enters the detector. The alarm is triggered by a microchip when the sensor no longer detects the alpha particles. An isotope of alpha radiation with a long half-life is used for smoke detectors so they don't need replacing often. Uses of alpha radiation. Household fire alarms. In the diagram at the bottom, alpha particles are stopped by the smoke, preventing the flow of current and triggering the alarm. Sterilization of equipment using gamma rays. Gamma radiation is widely used to sterilize medical equipment. Gamma is most suited to this because it is the most penetrating out of all the types of radiation. It is penetrating enough to irradiate all sides of the instruments. Instruments can be sterilized without removing the packaging. The source of gamma radiation used for sterilization has a half-life of around 5 years. This means the sterilization equipment does not need to be replaced often. Irradiating food to kill bacteria using gamma rays. Food can be irradiated to kill any microorganisms that are present on it. This makes the food last longer and reduces the risk of foodborne infections. Uses of gamma radiation. Killing bacteria. Food that has been irradiated carries this symbol, called the radura. Different countries allow different foods to be irradiated. Measuring the thickness of materials using different radiation. Beta radiation is most commonly used to measure the thickness of materials because it will be partially absorbed by most materials. Alpha particles are used for thinner materials because they have a lower penetrating power and are absorbed by a thin sheet of aluminium. Gamma radiation can be used for very thick materials because they have a higher penetrating power and are mostly absorbed by thick pieces of lead. A material moves across a radiation source. The particles that penetrate it are monitored using a detector above. The thickness of the material is monitored. If the material gets thicker, more particles will be absorbed by the material, meaning that less will get through and be detected by the detector. If the material gets thinner, the opposite happens. The machine makes adjustments to keep the thickness of the material constant. Radiation used to measure the thickness of materials has a half-life of many years, 10 to 20 years, so that the count rate remains relatively constant each day. Uses of radiation. Monitoring material thickness. Beta particles can be used to measure the thickness of thin materials such as paper, cardboard or aluminium foil. Diagnosis and treatment of cancer using gamma rays. Radiotherapy is the name given to the treatment of cancer using radiation. Chemotherapy is treatment using chemicals. Radiation can kill living cells. Some cells, such as bacteria and cancer cells, are more susceptible to radiation than others. Beams of gamma rays are directed at the cancerous tumor. Gamma rays are used because they can penetrate the body, reaching the tumor. The beams are moved around to minimize harm to healthy tissue whilst still being aimed at the tumor. Gamma radiation used in radiotherapy has a half-life of around 5 years. This means that it does not need to be replaced often within the machine that uses it. Uses of gamma radiation. Treatment of cancer. Radiation therapy to remove a tumor. A tracer is a radioactive isotope that can be used to track the movement of substances, like blood, around the body. A PET scan can detect the emissions from a tracer to diagnose cancer and determine the location of a tumor. The half-life of a tracer is several hours. This provides time for a scan to be conducted and then the radiation to leave the body quickly. Worked example. Use the diagram to explain why alpha radiation is used in smoke detectors, and beta or gamma radiation is not. Answer. Consider the different properties of alpha, beta and gamma. Alpha is the most weakly penetrating and strongest ionizer. Beta and gamma have stronger penetrating power and weaker ionizing power. If beta or gamma radiation were used in this situation, then they would pass straight through the smoke and the alarm would not go off. Therefore, since alpha is absorbed by smoke, and beta and gamma are not, this makes it most suitable for use in a smoke detector. Exam tip: if you are presented with an unfamiliar situation in your exam, don't panic. Just apply your understanding of the properties of alpha, beta and gamma radiation. Mainly think about the range, how far it can travel, and ionizing power of the radiation to help understand which radiation is used in which situation. Dangers of radioactivity. Ionizing nuclear radiation can damage living things such as human cells and tissues at high doses. This can include cell death, mutations, cancer. If the atoms that make up a DNA strand are ionized, then the DNA strand can be damaged. If the DNA is damaged, then the cell may die, or the DNA may be mutated when it is replicated. If a mutated cell replicates itself, then a tumor may develop. This is an example of cancer, which is a significant danger of radiation exposure. Ionizing DNA is a danger of radioactivity. Diagram showing the damage caused to DNA by ionizing radiation. Sometimes the cell is able to repair the DNA during replication successfully, but incorrect repairs can cause a mutation. Acute radiation exposure can have other serious symptoms. It can cause skin burns, similar to severe sunburn. Radiation can reduce the amount of white blood cells in the body, making a person more susceptible to infections by lowering their immune system. Because of this, it is very important to handle radioactive sources carefully. Safe storage. Radioactive materials are moved, used and stored in a safe way. Safe handling to minimize the dangers of radioactivity. The risks associated with handling radioactive sources can be minimized by following a few simple procedures. Store the sources in lead-lined boxes and keep them at a distance from people. Minimize the amount of time you handle sources and return them to their boxes as soon as you have finished using them. During use, keep yourself and others as far from the sources as possible. When handling the sources, do so at arm's length, using a pair of tongs. A sign indicating the dangers of radioactivity. Radioactivity warning sign. Safe transportation to minimize the dangers of radioactivity. Radioactive materials such as used nuclear fuel are transported in special containers called casks. These casks can withstand extreme conditions such as fire, cold, and being submerged in water. Disposing of radioactive waste to minimize the dangers of radioactivity. If an isotope has a long half-life, then a sample of it will decay slowly. Although it may not emit a lot of radiation, it will remain radioactive for a very long time. Sources with long half-life values present a risk of contamination for a much longer time. Radioactive waste with a long half-life is buried underground to prevent it from being released into the environment. Correct disposal of radioactive waste reduces the dangers of radioactivity. Radioactive waste with long half-lives is buried deep underground. Worked example. A student plans to use a gamma source to conduct an experiment. List 4 things that the student should do in order to minimize the risk to themselves when using the source. Answer: any 4 from. Keep the source in a lead-lined container until the time it is needed. Use tongs to move the source, rather than handling it directly. The source should be kept at as far a distance from the student as possible during the experiment. The time that the source is being used should be minimized. After the experiment, the student should wash their hands. The date and the time that the radiation has been used should be recorded. Safety precautions. Extended tier only. Safety precautions for all ionizing radiation include reducing exposure time, increasing the distance between the source and living tissue, using shielding to absorb radiation. Reducing exposure time reduces the dangers of radioactivity. Limiting the amount of time spent near a radioactive source reduces the amount of radiation dose received. The amount of radiation received by a person is called the dose and is measured in sieverts SV. 1 sievert is a very big dose of radiation. It would cause acute radiation poisoning. Increasing the distance reduces the dangers of radioactivity. Increasing the distance the radiation is away greatly reduces the size of the dose received. Using tongs instead of your hand when handling a radioactive source can help with this. Constructing nuclear power plants in remote areas increases their distance from people if there is a problem. Burying nuclear waste far from places where people live also increases the distance to people. Shielding reduces the dangers of radioactivity. Radiation shielding is a barrier placed between a radiation source and a person or area to protect them. The purpose of shielding is to limit exposure to radiation at a certain location or time. Barriers absorb the energy from radioactive sources. Barriers are normally made of lead, water or concrete. People handling radioactive sources should wear a lead apron to reduce their exposure. When X-rays are taken, the area around where the image is needed is shielded. The radiologist stands behind a barrier or leaves the room, reducing the dangers of radiation for a radiologist. A radiologist can stand behind a lead barrier to reduce the amount of radiation they are exposed to.